KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to focus on refraction at a rarer medium and then reflection of a plane wave by a plane surface. Okay ma? Right. So in our last class we learned that how a wave, especially here light wave refracts, how a light wave refracts when it meets a surface which separates both the medium, okay. One is optically rarer medium, another one is optically denser medium. So at the time what happens when light propagates or when light meets the surface which separates both the media in the form of wave. Right. Now we are going to discuss refraction at a rarer medium. Refraction at a rarer medium. In the bracket you can see that it is V2 is greater than V1. So speed of light in second medium is greater than speed of light in first medium. Okay. So here light is entering from denser medium to rarer medium. That is important. See here. So if you see the refraction of light in the form of wave, a refraction of light wave, first you try to understand the picture ma. So whatever I drew here, so you try to understand the picture. See this, it is AB. AB is the incident wave front, and this is what here it is C to E, CE is the refracted wave front. It is the AB is the incident wave front and CE is the refracted wave front. So the light wave is coming in this manner. It is going to incident at the surface at an angle of incidence I. It is in medium 1. Afterwards it is going to refract, right? So it is the angle of refraction. Okay. So from B to C you can write it as V1 into tau, because V1 is the speed of light in medium 1, that is denser medium, and V2 here you can see V2 is the speed of light in rarer medium, that is medium 2. Okay. So this is the distance travelled. BC is the distance travelled by a light wave in the time interval of tau. Here in the same time this is the distance travelled. By a light wave in rarer medium, that is medium 2. It is denser medium, it is rarer medium. So that automatically it is refracted wave front. It is as usual I told you incident wave front. Okay. So this is the normal to measure the angle of incidence and angle of refraction. So geometrical mathematics will give us when it is I, this is also I, when it is R, this is also R. This is all about the information. When light wave refracts when entering from denser medium to rarer medium, that is important here. Okay, next see this, the angle of refraction now be greater than the angle of incidence. This is the common situation, you know very well. Even when we studied the last chapter ray optics also, you know, when light ray enters from denser medium to rarer medium, what happens? Okay, angle of refraction will be greater than the angle of incidence. Okay, right. Next, however, here according to Snell's law, you know the laws of refraction. The first law is incident ray, refracted ray, normal lie in the same plane. The second law is the ratio of sine of angle of incidence to the sine of angle of refraction is constant. Okay, and here we are having two mediums, no, I mean two media. So one is rarer medium, another one is, okay, first is denser medium, then it is rarer medium. So you know the refractive index. So when you are writing this ratio sin I by sin r in terms of refractive index, right, that's we already know. We already written from previous class also, you can know, right. So now including that, that is what refractive index of one medium and second medium, we can write like this, no? N1 sin I is equal to N2 sin R. Otherwise, N1 by N2 is equal to sin I by sin R. N1 by N2 is equal to sin I by sin R, right? Okay. Now, we can define sin IC is equal to N2 by N1. If I is equal to IC, then sin R is equal to 1. R is equal to 90 degrees. Then automatically sin 90 is 1, no? Then sin R is equal to 1. So in this expression, just in place of I you put IC, then in place of R you put 90 degrees, right? Then automatically what will happen? The same equation will become like this. So here IC, it will be 1, though this N1 will go that side. So sin IC is equal to N2 by N1, right? So this situation we came across in the topic of total internal reflection and critical angle in our last chapter, ray optics. Okay, right. So when angle of incidence is equal to critical angle, when angle of incidence is equal to critical angle, then automatically sin R is equal to 1, R is equal to 90 degrees. But suppose if angle of incidence is greater than critical angle, then there will be no refraction. Total light will sense back into the same medium. That phenomena is called as total internal reflection. Okay. See here, the angle IC is known as critical angle, and for all angles of incidence, greater than critical angle, we will not have any refracted wave. For all angles of incidence greater than critical angle, we will not have any refracted wave, and the wave will undergo what is known as total internal reflection. Okay, right. So afterwards, after completion of this, we can see. So it is the situation happens in case of refraction at a rarer medium. Right? So in refraction at a rarer medium, what we discussed, how a wave is going to refract when it meets the surface which separates both the media. That is what optically denser medium and optically rarer medium. But here the discussion is the light wave is propagating from denser medium to rarer medium. So when it is propagating from denser medium to rarer medium, it bends away from the normal because of the speed difference, right? So that is what V2 is greater than V1. Speed of light in second medium is greater than speed of light in first medium. Okay. So as usually, according to the second law of refraction, that is N1 sin I is equal to N2 sin R. That is actually Snell's law, but that we are writing in terms of refractive indices of both the media. Then after completion of that, that is what N1 sin I is equal to N2 sin R. Afterwards, we can now define, that is sin IC is equal to N2 by N1. That is what, by using the concept of critical angle and total internal reflection. When I is equal to IC, r is equal to 90, sin r is equal to 1. Then the same thing, n1 sin I is equal to n2 sin r will become as sin IC is equal to n2 by n1. Afterwards, suppose if I is greater than IC means there is no refracted ray, the total light will reflect back into the same medium. That is the phenomenon of total internal reflection. Okay, right. Now we are going to see the next one, that is reflection of a plane wave by a plane surface. Right. Next continuation, next topic, reflection of a plane wave by a plane surface. Right. So what is reflection? Right. What is reflection? The phenomenon in which light wave sends back into the same medium. The phenomenon in which light wave sends back into the same medium is called as reflection. Okay, right. Now you observe this picture, what's happening here? So it is the surface, right? It is the plane surface. This side is rough surface, this side is reflected surface, right? So the wave is coming, the light wave is coming. It is what? Incident wavefront. Observe carefully. It is the incident wavefront, right? It is the reflected wavefront, right? So the incident wavefront is coming in this manner. This is the incident wave. The incident wavefront is coming in this manner. It is the angle of incidence, and this is the reflected wavefront. This is going in this manner after completion of incidence. Meanwhile, it is the angle of incidence and it is the angle of reflection. Angle of reflection. Just now I told you what is the definition of reflection, right? How can we define the word reflection? Now I am saying the laws of reflection also. What are the laws of reflection? Angle of incidence is equal to angle of reflection. Next, what is the second law of reflection? Incident ray, reflected ray, normal lie in the same plane. So these two are the laws of reflection. So here also when the light behaves or when the light travels in the form of wave, here also both laws of reflection were satisfied. See here, Mn is the surface, right? So A is the point, right? So here B is the, right? So AB is the, see here, AB is the incident wavefront, and this is what CE is the reflected wavefront. Reflected wavefront, angle of incidence and angle of reflection. Okay. So here, if you observe carefully, here you can understood how the light wave is going to reflect. How the light wave is going to reflect. Okay. See this. A plane wave AB incident at an angle I on a reflecting surface Mn. Mn is the reflecting surface. From the figure, this is the figure, right? From the figure, what can we write, ma? From the figure, you can write it as BC is equal to V into tau. V is the speed of light here. V is the speed of light in this medium. Tau is the time taken to move from here to there, from B to C. Then, you know very well, speed is equal to distance by time. Distance is equal to speed into time. So, BC is equal to V into tau. Here, V is the, I already told you, V is the speed of the wave in that medium, and tau represents the time taken by the wavefront to advance from the point B to C. So, you should not take time from here to here. It is just an indication, that is the arrow mark in which direction the light ray is going to incident, right? That is the only thing, but time from B to C only you have to take. To write distance BC is equal to V into tau, you have to take the time from B to C only. Okay, right. Next, in order to construct the reflected wavefront, so this is the reflected wavefront. In order to construct the reflected wavefront, we draw a sphere of radius V into tau. We draw a sphere of radius, because you know very well in the starting of this chapter I told you, when we throw a stone, how the waves are going to originate and how they will travel, and what about the shape of the wavefront, right? And how the spherical wavefront became as a plane wavefront. That and all we will discuss in the starting of this chapter, at the starting of this chapter. Okay, right. So now, in order to construct the reflected wavefront, we draw a sphere of radius v into tau from the point A, as shown in the figure, right. Let CE represent, this is C, this is E. So CE represent the tangent plane drawn from the point C to this sphere. See here. So this is that, right. So this is that we are drawing now from C to E. So CE is the reflected wavefront, right. Now we can write it as AE is equal to BC is equal to VT. AE is equal to BC is equal to V into tau. We are taking the same time, that is important. So you may have a doubt. Why we are BC is equal to V into tau, okay, but why we are writing AE is equal to BC is equal to V into tau means we are taking the same amount of time. We are taking the same amount of time. Then only we can write. Here we are writing based on the geometrical properties also, right? Based on the geometrical properties and geometrical mathematics also you can write, but conceptually we are taking the same time. Next, from the triangles, see here, there are two triangles, EAC and BAC. From these two triangles, because of these two triangles are congruent triangles, because of congruency, you can write angle of I is equal to angle of R. Angle of I is equal to angle of R. So it is the first law of reflection now. It is the first law of reflection. Okay, right. Next, what is the second law of reflection? Here, incident wavefront, reflected wavefront, normal should lie in the same plane. Yes, of course it is correct. So practically, when we experienced this experiment, we can prove, right? So first law we proved mathematically. So geometrical mathematics, right? And second law is also correct. You can experience by the experiment, right? Next, what I am saying is, we have the laws of reflection and refraction, right? So yesterday, previous class we discussed refraction of light wave when it enters from rarer medium to denser medium. In this class, we discussed the refraction of a light wave when it enters from denser medium to rarer medium, right? So now we discussed reflection of a plane wave, that is what light wave, right? So with these all the things we discussed the laws of reflection and refraction, okay, right. But at the same time, suppose if the light is going to meet a prism, if the light is going to meet a convex lens, if the light is going to meet a concave mirror, what will happen? Because these are also same thing now, because these are all just having different shapes. So what will happen there, that we have to discuss. Okay ma? See here, observe carefully. See, suppose when a light is going to meet, right? When a light is going to meet a prism, see this is the case, right? Here what will happen? So it is the incident plane wave, it is the prism, so it is what? Output, right? So it is the wavefront, it is the plane wave, it is the wave which came out after passing through a prism. There is a difference between this and this now. So what is the difference? So this part of the wave travel more distance, this part of the wave travels less. So what is the reason? Here the thickness is less now, here the thickness is more now. So it takes more time to travel from here to there, right? Here in the same time, because of less thickness, because of thin, this part is thin and this part is more thick. That is the reason. The wavefront, the output of this incident plane wave will be like this. This is what as shown in the figure. Similarly, you go for, right? And one more important thing is here it is a glass prism, no. So glass is the denser medium when compared to the air. Glass is optically denser medium. Okay, right. So you know very well what happens to the speed of light when it enters from rarer medium to denser medium, right? So speed of light waves in a lens, speed of light waves is less in glass, no. When compared to the air, speed of light waves is less in glass. The lower portion of the incoming wavefront, this is the incoming wavefront, ma. The lower portion of the incoming wavefront will get delayed, resulting in a tilt in the emerging wavefront. This is the emerging wavefront. There is a tilt. There is a tilt because the speed of light waves in a glass is less when compared to the speed of light wave in air. Okay. So we consider, after completion of that, you just consider a convex lens. You just observe the behavior of light wave, how it is going to propagate and how it will become. So emergent wavefront, this is the emergent wavefront, ma. It is the incident plane wave, incident plane wavefront, and it is the emergent wavefront. Okay. So these three pictures are separate, that's why I drew here thick lines. Okay. So this picture is in case of prism what happens, in case of convex lens what happens, and in case of concave mirror. Okay, right. See this. So in case of convex lens, see this is the this is what top part. Okay, it is the middle part and it is the bottom part of incident plane wavefront. See here, if you see the convex lens, here it is thin, here it is thick, here it is thin, and here we have air molecules, and here it is glass. Okay, again here we have air molecules. Okay, see here, the incident plane wavefront is going to meet the surface because of thin, because of, even though it is made up of glass, so convex lens is made up of glass, because of thin, because of thick, and again because of thin. See here. So it is the part of plane, incident plane. Actually it is emergent wavefront, ma, but anyhow it is the bottom part, no. It is the top part, it is the central part, right? See here, what is the shape of the emergent wavefront? It is a spherical shaped wavefront. Okay, so here you can expect the focus for this spherical shaped wavefront. Okay, so that only he is writing here, a spherical wavefront of radius small f. So it happens in case of convex lens. Similarly, if you take concave mirror of radius capital R, right? So it is the incident plane wave. Incident plane wave is same in all three cases, but the application only different. Here it is prism, and it is convex lens, and it is concave mirror, right? So what happens with the concave mirror? We studied in our last chapter, that is ray optics. So reflection in case of spherical surfaces, right? So it is the incident plane wave. It is going to meet the surface. I mean, it is going to meet the curved surface, curved reflected surface due to the concave mirror. But after completion of that, what will happen? It has to reflect, no? It has to reflect. So that's why the situation, the spherical reflected surface, otherwise curved reflected surface, will provide this as the output. That is what emergent wavefront. This is incident plane wavefront. This is emergent wavefront, which is available in the spherical shape, right? So spherical wavefront of radius r/2. It is what concave mirror. It is what concave mirror. So in all these cases, you have to keep in mind, whether it is prism, or convex lens or concave mirror, you have to keep in mind total time taken from point on the object. Total time taken from point on the object to the corresponding point on the image. To the corresponding point on the image is the same. If you measured in any way, so here also, here or here or here, wherever you measure, the time taken from point on the object to the corresponding point on the image is same. Okay. Suppose for example, whatever it may be, I need not to point out separately whether it is prism or convex lens or concave mirror, right? It is the same. Okay. So, and another reason is, You know very well, when the speed of light is entering from rarer medium to denser medium, optically rarer medium to the optically denser medium, it will be decreased. It will be decreased. Then again, when it enters from denser medium to the rarer medium, again it will be increased. That is the second reason. Okay, right. So in this class, our concentration, our concentration and our focus is refraction at a rarer medium. So light wave, I am not, see when I was explaining, I used the word light wave because the same thing we discussed in our previous chapter, ray optics, but there the light is in the form of ray. There the light is in the form of ray, but here the light is in the form of wave. So even though light is in the form of wave, it satisfied all reflection, refraction and loss of reflection and loss of refraction also. Okay. So in this class we discussed when a light wave is going to propagate from denser medium to the rarer medium, how it behaves, how it satisfied the loss of refraction. Okay. And what about critical angle and what about total internal reflection, that we discussed. Next, reflection of a plane wave by a plane surface. Reflection of a plane wave by a plane surface. Here we discussed about reflection and loss of reflection also. Loss of reflection also, that is angle of incidence is equal to angle of reflection, and incident ray, reflected ray, incident wavefront, reflected wavefront and normal lie in the same plane. Okay. Afterwards, we came to discuss what happens to the incident plane wavefront when it is going to pass through a prism, when it is going to pass through a convex lens, when it is going to incident on the concave mirror, which is the curved reflected surface. Okay. Thank you. We will continue in the next class.